You know, for more than half a century, we've been trying to build a star right here on Earth to harness the very same power that fuels our sun. And just recently, for the very first time, we actually did it. So what we're going to do here is break down that incredible achievement and then take a hard look at the monumental journey that's still ahead. That's what scientists have called this for decades. Not just a goal, but a quest, kind of like searching for the Holy Grail. It's that moment where we could finally prove that it was possible to get more energy out of a fusion reaction than we had to put in to get it started. Because, let's be real, achieving this ignition in a lab is one thing, but actually powering our world with it, that's a whole other ballgame. This is really the story of a 50-year-old problem finally getting solved, only to reveal an even bigger one hiding right behind it. Let's start with why we're even doing this. So first things first, why is fusion such a big deal? What's this incredible promise that has captivated scientists for generations? Well, it all comes down to the fundamental process that literally makes the universe shine. This is basically the engine of the cosmos. See, instead of splitting heavy atoms apart, which is what today's nuclear power plants do, fusion forces light atoms, like different kinds of hydrogen, to merge together. This marriage of atoms releases a truly staggering amount of energy. And when you put them side by side like this, the difference is just night and day. Fission, on the left, it works, but it leaves behind radioactive waste that's dangerous for thousands of years. Fusion, on the other hand, promises just this incredible amount of power with zero greenhouse gas emissions and very little long-term radioactive waste. It is, for sure, the clean energy dream.
But there was always a catch, a huge one. To get these atoms to fuse, you need unbelievable temperatures and pressures. We're talking conditions hotter than the core of the sun. So for over 50 years, the challenge was really simple to say, but almost impossible to do. Could we get more energy out of the reaction than the energy we use to kickstart it? That's what they call scientific break-even.
And that brings us to a very specific date and a very specific place, where after all those decades of trying, that massive barrier was finally broken.
I mean, just try to get your head around this. At the National Ignition Facility in California, scientists aimed 192 of the most powerful lasers in the world. We're talking a building the size of 3 football fields, and focused them all onto a target smaller than a single peppercorn. For just a split second, they literally created a star in a bottle.
So what happened in that tiny fraction of a second? Did they actually do it? Did they hit break even? All right, let's look at the numbers. Okay, first up, the energy in those 192 lasers slammed the target with 2.05 megajoules of energy. That's how much it took to get the reaction going. So remember that number, 2.05. And the energy that came blasting out? The fusion reaction unleashed 3.1 megajoules. That's over 50% more energy than what they put in. And that was the moment. That was the holy grail. For the very first time, anywhere, a fusion reaction produced a net energy gain. The 50-year-old science problem was solved. It worked. But, you know, when you answer a scientific question that big, you often uncover a whole new set of questions that are arguably even harder. How in the world do you turn this single microscopic flash of energy into a power plant that can light up a city 24/7? This quote from researchers at MIT's Plasma Science and Fusion Center, man, it just lays out the new reality so clearly. They're basically saying, great, you proved it's possible. The problem is, the stuff we need to build a real-world reactor, it hasn't even been invented yet. And to really get why, you have to appreciate just how punishing the inside of a fusion reactor would be. It is, without a doubt, one of the most extreme, unforgiving environments humans have ever even tried to create, let alone contain. So what you're seeing here is a common design for a reactor. It's called a tokamak. Think of it like a giant magnetic donut. That glowing ring in the center is the plasma. That's our star in a bottle. But everything else surrounding it, all that machinery, has one impossible job: survive conditions that would vaporize pretty much any material we know of. And here's that harsh reality. The materials right on the inner wall have to take heat that's hotter than the sun. They're also getting bombarded by a constant stream of super high energy neutrons. Think of it like microscopic cannonballs that are literally knocking atoms out of place, making the whole structure brittle. On top of that, they have to deal with immense magnetic forces, resist being eaten away by coolants, and, oh yeah, contain the radioactive fuel called tritium with almost perfect efficiency. There is no single material today that can survive all of that for very long. So how should we even think about the timeline for all this? Well, probably the best analogy comes from the history of aviation. The big scientific breakthrough, it was just the first step on a very, very long runway. Think about it like this. The NIF ignition in 2022 was our Wright brothers' first flight. It was the proof of concept. It showed it was possible. But getting from that rickety plane to the first real commercial jetliners, the Boeing 707s of the 1950s, that took about 50 years. And for fusion to become a huge part of our global energy system, like the Boeing 747 transformed travel, we might be looking at the 2060s or even later. And that's really the key takeaway here. For 50 years, fusion was a physics problem. The question was, can it even work? Well, we answered that question. It's yes. Now, the focus has totally shifted. It's become a massive materials science and engineering problem. The question is no longer, can it work? But can we build it to last? And can we do it affordably and safely? Which kind of leaves us with this one last thought. Proving a plane can fly is a world away from creating the entire global infrastructure of airports and supply chains and safety regulations that make air travel a normal part of our lives. That fusion breakthrough was our first flight. Now begins the immense, incredible task of building the airport.
Echoes of the past, visions of tomorrow.